Let's get started. So if you think about chemistry and physics, then one concept that pops up at some point are resonances. They define where you absorb energy, where you emit energy, but also how you transfer energy within the system. So if you think of a donor-acceptor system, first the resonant energy transfer depends, as the name suggests, strongly on the evolved resonances inside the system. So one natural way to interact with resonances and potentially also control them is then light. And if you typically take a molecule or whatever system you have and you place it in free space, then we talk mostly about the kind of inelastic scattering process. So it's a very weak interaction between light and matter. You have a material excitation, has a certain line width that comes from, well, basically the photonic continuum in which it is embedded. And then you have fluorescence, for instance. You can change this to some extent by confining the optical fields. So we talk often here about a cavity and not escamille, but really it's a cavity that confines electromagnetic modes by basically enforcing certain set of boundary conditions to those modes. And that means nothing else than carving specific discrete eigenmodes out of this photonic continuum. So you only allow certain eigenmodes to exist. And those can now interact more coherently, more strongly with the molecules that you place inside the system. The interaction strength depends on the number of molecules that you place into the volume. So you can see that either by decreasing the volume of the cavity, going, for instance, to small plasmonic cavities, or by putting a lot of molecules inside that have very strong dipole moment, you can reach a very strong interaction. And if it's sufficiently strong that you really see a hybridization between light and matter excitation, then you talk about polaritons. And those polaritons can be used in various different platforms for different applications. One is, for instance, polaritonic chemistry. So here in this experiment that will reappear during this talk a couple of times, the idea is that you have this deprotection reaction of this PTA complex here. It usually breaks the silicon-carbon bond. And now I take the infrared cavity, I tune it in resonance to the silicon-carbon vibration of the molecule, so one of the vibrations here. I get my polytonic states, my strong coupling between light and matter. And precisely under this configuration, I can see that my reactant is available for a much longer time. So the reaction, so to say, is slowed down, inhibited under vibrational strong coupling. There are also other possible platforms that are very interesting, for instance, plasmonic systems. And here it's really a mass of different possible processes that play a role. We have very strong optical fields in the vicinity of those plasmonic systems. They are commonly used for sensing, but you can also use them for strong decoupling to nearby molecules. You can also leverage the electrons, so the charge carriers that you generate after exciting those plasmonic particles, and use them for catalysis. So you really have like a very broad tool set that you can apply to control chemistry with both of those systems. And what they have in common is that they're pretty challenging to describe if you aim for chemical accuracy in quotation marks here. So we have a really multi-scale, multi-time scale problem at hand where we have to describe the molecules, the chemical reaction of those molecules, potentially charge transfer happens over femtoseconds. And then also those big systems that are, so to say, giving rise to those more microscopic features that are affecting the chemistry in the end. And what we try to do is develop ab initio QED to tackle this. The basic current state of the community, or kind of where we are heading, is very simple. We take quantum chemistry methods that are first principles, and we basically add photons to it. So, for example, we extend density functional theory by the quantum electromagnetic density, by the quantum electromagnetic degrees of freedom. So that's what it's called in the end, QDFT, quantum electromagnetic density functional theory. But you can do the same for coupled cluster or other approaches. The bottom line is really that you try to be as ab initio as possible, and you add the photons on top to understand better how the photons can control the chemistry, for instance. So I want to focus on the talk a bit more on one special aspect here that plays a role, vibrational strong coupling. And as said earlier in the introduction slides, the idea here is that you have a chemical reaction that undergoes as usual, and then you confine it into an optical cavity, an infrared cavity to be more precise, coupled to one of the vibrational modes inside the system, and in this way can control the speed of the reaction or potentially also the product that comes out of this reaction. And we have this nice experiment. It was really one of the first ones. By now, there's plenty of others as well that show, for instance, also a catalyzing effect or a steering effect inside the cavity. But this one was really the first one and probably also the most repeated one, most well done one. And we clearly see this inhibition under vibrational strong coupling. Now, the beauty of our ab initio theory is that we can really try to one-to-one simulate this. So you expect this kind of potential energy landscape where you have initial state, we have some intermediate, and then some transition state that we have to overcome for the chemical reaction to appear. And we really start with this initial configuration of a PTA molecule and then being attacked by a fluoride anion from the solvent. So basically it should go on a minimum and then at some point break apart. In order to simulate this, we have to, of course, perform some approximations. Right? So ab initio does not mean that you don't perform any approximation. It just means that you try to be not too screwed in the perspective that you apply those approximations. We describe the electrons with QDFT, so this extension of DFT. Nuclei are classical, following the Ehrenfest equation of motions, and the cavity are Maxwell's equation of motions, so also classical fields here. And probably the most severe approximation is that we only describe a single molecule in a single cavity mode. So this is really a severe limitation of our descriptions, and I will go later about methods that we would like to apply in the future of trying to circumvent this limitation. But let's focus on the simple model first here. And this is what we get. So we simulate 3 different trajectories, and they're illustrated here on the potential surface. So it's not MD, I said it's Ehrenfest dynamics for the nuclei, but it's just for visualization on the potential surface here. And you can nicely see that all 3 trajectories, they're entering this local minimum. So this PTAF minus pentavalent complex here, basically a silicon fluoride distance just reduced. And then at some point, the outside the cavity and off resonant configurations, they cross the transition state and breaking the silicon carbon bond, which is the reactive bond in this case. Yeah. However, if you're on resonance with the cavity, then you see that you stay trapped in this local minimum. So something is the cavity doing here to kind of inhibit crossing this transition state. And when I say resonant, I should probably be as fair and tell you what resonance means. So in the experiment, they looked at like 860 inverse centimeters. So this resonance here, which is this vibrational excitation that you can see in the vibration spectrum down here. And here on the top, you see the average silicon fluoride, silicon carbon distance. So it's something like a prime or a figure of merit for the reactivity of the system. And you can see that outside the cavity, you have kind of this baseline, and then everything is inhibiting. But there are certain features appearing here that clearly show that for given frequencies of your cavity, and you can imagine that you can change the frequency of your cavity by just changing the distance between the mirrors, you can kind of more selectively inhibit the process for the reactivity here. And the strongest effect always appears where you have a strong infrared active mode with a strong contribution of the silicon carbon bond. Makes a lot of sense, right? So you want to have a strong coupling between light and matter, but you also want to have that the mode that you couple to is really relevant for the reaction. So that's why you have this combination that seems to be very dominant here in the effect. So you can try to understand this a bit more in detail of what potentially the mechanism is here. And what I've shown you here is the difference in mode occupation between the resonant cavity and the off-resonant cavity. So basically, you can see that a lot of vibrational energy is kind of redistributed during the chemical reaction inside the system. And some modes are more strongly affected than others. Those modes that are more strongly affected than others are the ones that have a strong silicon carbon character. Again, makes a lot of sense, right? Because it's involved in the chemical reaction. And you can see that between certain modes, between 850, for instance, 540, you have a somewhat coherent exchange of energy, actually, via the cavity over a certain time frame. But most of the energy is kind of loosely getting distributed inside the system. So what's the running idea of the mechanism so far is that if you think of what the chemical reaction should process like, right? You thermally excite the system in some way. Like the fluoride is bunching to the system, kind of an inelastic scattering process. You deposit a lot of energy, and now the normal modes start to kind of reorganize this energy in a certain way. That means that at some point, when you attempt to break this bond, you need a certain superposition of those modes that really want to elongate the molecule in this axis. This means that you have a strong current inside your system. The strong current, think of Maxwell, current induces an optical field. The current can interact very effectively with the cavity. So you have a very strong light-matter interaction at this moment, which means that the cavity can very effectively absorb energy out of the molecule. It really takes energy out, and in this way effectively reduces the temperature for the reactive molecule. So it kind of cools it down. And in the end, it's kind of a Robin Hood effect, where reactive molecules, the hottest molecules, are getting cooled down by the cavity, and this energy is redistributed in a more equal fashion. It might just be stored for a short time in the cavity. It might get lost to the environment. It might be redistributed to other molecules or simply to other vibrational modes in the energetic vicinity. So I think this was a very important first step, trying to understand this, but we have a couple of limitations in this method. One really severe one is that the statistics is very limited. So we've only had like 30 trajectories here, which basically gives us more like a taste, but not a very reliable estimate of what could happen here. So the next step, we try to kind of approach this problem by combining machining potentials that we train for energies, forces, and dipole moments for those molecules, and now combine this with molecular dynamics, including the cavity that is also propagated, again, with Maxwell. So it's basically now molecular dynamics plus the cavity, and the forces that drive the dynamic of the molecule are now combined force of the standard forces from the potential surface and the cavity forces that are basically nothing else than driving with the cavity the gradient of the dipole moment. And then we get this result here. So it's a lot of information. Let me guide you through it. On the top left, you have the infrared spectrum, and you can see nicely that for higher temperatures, you have more oscillations and broader peaks, also slight red and blue shifts, but that's not too relevant here. And then you can go over to figure B here, where the difference in silicon carbon power spectrum is plotted. So this basically just means that if I look at the silicon carbon bond, it will oscillate at a certain frequency, right? And depending on which mode it contributes to, it will have a different frequency. And you can nicely see that inside the cavity, you decrease it at certain resonances where the cavity agrees in frequency with the vibrational mode. And it will kind of shift this intensity, the silicon carbon intensity, to the hybrid, to the polaritonic states in the vicinity. So you see those nice avoided crossings appearing here, where you also have, because there are different contributions of the silicon carbon bond, they're differently in intensity. What really stands out is that you have those low energy features, and kind of intuitively, if something is very slowly modifying in the reactive bond, it should have an impact on the chemical reactivity. Right? And this is indeed what you can see here. If you look at the rate for the system, for the different cavity frequencies, you can nicely see that you have certain domains that are now catalyzing, others that are inhibiting. And it's not as clear as before in the previous study, where we used the Ehrenfest plus DFT plus Maxwell in our studies. You can look at certain frequencies. We would like to understand better, like what is the change in enthalpy and entropy, and perform an airing plot. And this is basically the result here. The experimental relevant domain is again at 856 inverse centimeters, so the green line here. And if you look at those results, it's really for the first time in qualitative agreement with the experiment. Not quantitative, but qualitatively, it's for the first time in agreement. So we see an increase in enthalpy and entropy here as an experiment. Now, the question is, of course, how does it come that it's not purely inhibiting anymore, right? The only thing that we changed was that we went from, so to say, full ab initio Ehrenfest plus QDFT to MLPs plus MD. And if you rerun with the exact same initial conditions as we have used in the previous study, now with our MLP plus MD approach, you can see that the overall trend for the change in reactivity compared here to a different metric, but I mean, they are somewhat comparable, is somewhat consistent. But we have this massive offset. And that is something that we don't really understand yet, that we still have to explore more in the future. One possible reason of what could happen here is that we're not really accounting for the effect that the cavity has on the electronic degrees of freedom of the molecule. You can imagine if you have a very strong field in your cavity, it basically acts like a static polarizing field on the electrons. The electrons moving much faster than the nuclei, right? So if you have a certain configuration of cavity plus nuclei, this will be almost static for the electrons. And that's really not something that we're accounting for. So this kind of polarization correction that we would need to account for is not included yet. This might be one reason. And it might be connected to this artifact that we're using a single molecule to simulate the chemical reactivity here. Well, in practice, is of course many molecules that kind of collectively interact with this cavity. What we definitely need is more experimental data, because at the moment we only have data at like 860 inverse centimeters, and both of our descriptions give us here an inhibiting effect. And as said, it's consistent with the experiment. But it would be extremely helpful to have also more data outside this domain. So the take home for the first part is that we have this inhibition under vibration strong coupling, which is in qualitative agreement with the experiment. We have this change in enthalpy or increase in enthalpy and entropy for the inhibiting reaction in this case here. And we have a decent understanding of the possible mechanism, which basically is that we change how vibrational energy is redistributed inside the system, effectively cooling the molecule. So this kind of Robin Hood-like effect. But we definitely need more, kind of especially overcoming this distinction between the current theory, single molecule, to the experimental conditions, to really understand it in detail. With this, I would like to basically keep the idea in mind. So we can control the spectrum of the molecule with strong coupling. We control how energy is flowing inside the molecule or between different molecules. And this way, control the reactivity. Keep this idea, and now we can transfer it to a different setup. We want to make it enantiomer-selective. So what do you need to transfer this idea to enantiomer-selective processes? To make it enantiomer-selective, first, we need a cavity that is now confining only one-handedness of the field. Okay, so if you take a normal gold mirror, for instance, then I come in with a certain circular polarization. I reflect at the surface. I invert the propagation direction, but the circular polarization is retained, which means that the handedness of the field is inverted. So this is a basic principle of reflection symmetry on those surfaces. So what we need to do is we break the symmetry, basically. We need to convert left-handed into right-handed circular polarization when you approach the surface. And you can do this by designing certain metamaterials that include, for instance, those kind of drilled ellipsoids into a certain gold surface here. And given this configuration, you can really confine chiral eigenmodes in this metamaterial cavity here. And this is a simplified description here. You can really see that you have this kind of corkscrew nature, cosine and sines here. And the relationship, if it's left or right-handed, so if your handedness of the field is left or right-handed, basically depends on if it's pi over 2 advanced or retarded, the magnetic field, compared to the electric field. So this is included in the factor lambda here. And the beautiful thing is now that if I calculate just purely the vacuum chirality density, so how chirally polarized is my vacuum, the vacuum fluctuations of the field, then I will find that indeed they're chiral, right? No big surprise, really, if you think about it, because we confine now mostly one-handedness inside this cavity, while the other one is basically just going through. So there's no confinement, no enhancement, so to say. But this means that if we now place molecules inside the system, and this is not fully ab initio, it's really simple. Assume just the simplest imagination for molecules, harmonic oscillators, or two-level systems. Important thing is that they have an electric and a magnetic dipole moment. So if you now place them inside the system, you would expect again strong coupling, right? And indeed, we find the same basic principles as before. So again, it scales with the amount of polarizable material that you place inside this cavity. But then you also have the second factor, 1 plus lambda chi. I said lambda is the handedness of the field, so it's plus or minus 1 for transversal fields. And then chi is the degree of chirality for the molecule. So basically the proportionality between electric and magnetic dipole moment. So if they're now of opposite sign, so if the molecule is left-handed and the field is also left-handed, well, then this will increase this one here, basically, right? I increase the interaction strength between light and matter. While if they're of opposite sign, so if they're mismatched, then I will decrease the interaction strength. So I can talk selectively to one enantiomer stronger than to the other one. And I can use this now in multiple different ways. One possible approach is to really control even just lifetimes. If you think of fluorescence, for instance, then the rate of fluorescence depends very much on the optical environment you confine it in, the molecule, for instance. So that means if I talk more strongly to one enantiomer, then this will have an enhanced fluorescence rate compared to the other one. If I reach strong coupling, so I create those polytonic states and we split them in energy, then I can, for instance, more selectively excite one of the two enantiomers. I can transfer those vibration strong coupling ideas that I've shown you before, now also to enantiomer-selective reactions. Or you can look at really fundamental features like homochirality, trying to understand better why is one chemical species, one enantiomer, more present in our body, for instance, than another one. Here we can really selectively and very controlled break the symmetry in the vacuum, which would be extremely useful for understanding those processes. I think I'm running out of time. So last aspect. So there is still open challenges that we will fix in the future. And one is very much that the degree of chirality is for many molecules very small. So that means that this kind of selectivity is also small. And one possible fix is to move away from only polaritonics, transversal fields, to combine this with longitudinal fields. So mix chiral polaritonics with chiral plasmonics, because this allows us to really boost this factor lambda here if you have longitudinal fields, and in this way be more selective in the future. So I will skip the next part because I'm running out of time. Basically, the bottom line is that we can also control plasmonic catalysis by using vibration strong coupling, electronic strong coupling. But I think I would like to come to the conclusion here. So I've demonstrated that vibration strong coupling can control the chemistry. We have now qualitative agreement with the experiment. We have a decent understanding of the reaction mechanism that is basically controlling how vibrational energy is flowing within the system by using the optical degrees of freedom. But there are still open questions, like how do we account properly for the polarization? Is this relevant? Is it important to treat many molecules? For sure, to get a quantitative agreement, but maybe the qualitative agreement that we find is already sufficient for a single molecule. So many open questions and a lot of method development that will be involved here. It's also interesting to mention or highlight that, of course, there is an interaction with the solvation shell around those molecules, right? So if I control the polarization, for instance, of those molecules by placing it inside the cavity, then this will have an effect on aggregation and solvation dynamics. So we have some studies on this here. I've also shown you that you can transfer this to chiral systems and make it Enantiomer-Selective. And I have not shown you, but maybe you can believe me or read up on it, that we can, to some extent, also control plasmonic catalysis. In this case here, boosted by factor 6 to 7, roughly. And then there's a lot of method development that is still to be done here, just simply because this ab initio QED topic is a very fresh domain still. Thank you for your attention, and I'm looking forward to your questions.